In this problem, we're looking at an airplane climbing and descending along curved paths. NASA uses an airplane called the Comet. That's not its official name, but its affectionate name based on what happens to a lot of its occupants when they're riding in it. But this plane actually simulates varying amounts of gravity based on how it is accelerating around these curved paths. So let's look at the first curve. Here at this point in part A, the plane is flying over the top of the curved path, and at this point, the passengers are experiencing 0 Gs. Remember, 0 Gs doesn't mean gravity has turned off, but the feeling of gravity that we get when we have a ground or surface underneath us, it goes away. So these passengers, the plane and everything in it, are actually in free fall at this point at the top of the path. So given the radius of that curve, how fast must this plane be traveling at that first position? What is V1? So let's look at it from the perspective of a passenger. And we're going to look at the free body diagram of the passenger. That passenger is inside the fuselage. Now, let's say the passenger is just floating around. So the surface is here. So what is the forces acting on that passenger? Well, the passenger is actually, along with the plane, here's the plane, they're actually traveling in a curved path. Right? And so we know by definition that they are accelerating. Well, what is causing that acceleration? Well, the force acting on that person is the force of gravity. Now, because they are floating and not feeling any weight, then we know that the normal force is actually 0. And they're inside the fuselage, so there's no air resistance because the plane is taking that. So we really have only one force, right? And we can look at, well, what is their acceleration at that point? Well, if there is only one force, that force, Fg, right, Newton's second law says F equals ma. Well, that's going to cause that mass to accelerate. Except in this case, we are moving in a curved path. So this is a special kind of acceleration. It is a centripetal acceleration. But we also know something else, right? We know the acceleration due to gravity. In this particular problem, we know that AC has to equal 9.8. AC is equal to 9.8 meters per second squared because they're in free fall. It is the only force acting on them, and so they are falling freely and accelerating downward. And in fact, that's exactly what's happening to these passengers, and it's exactly what you would feel like if you were falling in an elevator in free fall. You would be accelerating downward at 9.8 meters per second squared, and you'd feel weightless. Right? So what velocity would cause that? Well, in circular motion, we know that the acceleration, the centripetal acceleration, is equal to the square of the velocity over the radius. And since we know that the centripetal acceleration is 9.8 meters per second squared, and notice normally it's downward, right? However, if the center of the circle is in here, then we know that this is the positive direction. It is an inward acceleration, and inward is positive, right? So again, when we're working in circles, we look at in and out. This force is acting towards the center of the circle, so we would say it is a centripetal force, right? And we know the radius. What we don't know is the velocity. And so when I put the radius in here, it's 800 meters, and now it's an algebra problem. So let's solve for v and find out how fast this airplane's going. We can multiply both sides by 800 meters. So I'm going to multiply by 800 meters. And when I do that, look at what happens to our units. And that goes away. You get v squared on the right side. And you get 9.8 times 800. 9.8 times 800. You get 7840. 7840. Look at the units. I have meters times meters per second squared. That's meters squared per second squared. And when we solve for v, we would take the square root of both sides and look at what happens to my units. Right? Meters squared per second squared about the square root of that is meters per second. So I'm going to take the square root of the answer, and I'm going to get 88.5 meters per second. The velocity of the plane at this point needs to be 88.5 meters per second at that point. That's what V1 is. So we now know how fast that plane is going through the top of that arc in order to feel weightless. Now what happens at the bottom? So as this plane comes down, and changes direction and starts climbing again, we pass through the bottom of this second circle with a new radius, r2. We now know this plane is traveling faster, right? It's been gaining velocity in free fall, so it's going faster than 88 meters per second. At this lowest point, what did the actual riders feel? Well, let's draw that free body diagram again for part B. So in part B, we now have the riders. And let's draw the fuselage of the plane again. And that rider now is accelerating which way? Well, the center of the circle, here's our circular path, the center of the circle is up here, which means we need, in order to be curving, a net force that acts inward. Well, this passenger still has gravity acting down. Well, what force is going to be there to push up on this passenger such that they have a net force inward in order to accelerate along that curve? Well, that's going to be the surface of the fuselage. All right, so the floor of the plane is going to be pushing up. We'll call that a normal force. And if we know what the normal force is, NFG, we can actually determine the number of G's. All right, so we know that this plane is accelerating. We have an inward acceleration, a positive acceleration, and we know that the sum of all the forces in the centripetal direction cause a mass to accelerate centripetally. We know that the forces involved, we have a normal force, we have a weight, Fg. We're just adding forces like we've done. Those are both forces that point along that line to the center of the circle. And that is equal to m. And remember, AC is just v squared over r. All right, so that's going to be the equation that governs what we need to know. And we ultimately want to know what is the ratio of the normal force and gravity. Well, let's continue to plug in some pieces here. We know that the radius is 600. We know the velocity, so we actually know the centripetal acceleration. All right, so let's plug in some more things here. We know Fn is unknown. Let's add Fg. And v squared over r. V squared would be 600 squared. And the radius r2 is given at, the radius is 600. The velocity is 120. So we'll square the velocity. 120 over 600. All right, it seems like we're missing a lot here, right? Well, what else do we know? Well, we don't know the passenger's mass. The question would be, if there are multiple passengers, would they feel something different, right? Well, let's give our passenger a mass. Let's say this guy has a mass of 100 kilograms, a nice big astronaut. All right, so let's plug in what we know then. Well, then we now know what Fg is, right? Fg is always equal to the object's mass times the acceleration due to gravity. So in this case, it would be 100 kilograms, and the acceleration would be 9.8 meters per second squared. So I get 980. Fg is 980 newtons. Right? Now, what direction is that? Fg is outward, so I'm going to make it negative. Fg is negative 980 because it points outward. All right. Let's plug in some other things here. Let's see what the normal. So now, if you plug in those values here, Fg is a negative. It's outward at 980 newtons. We now have a mass. Let's put 100 in here times that 120 squared over 600. In fact, I'm going to actually calculate that here. What's 120 over the 600? This is the centripetal acceleration is 24. I'm going to write that in here. This is actually 24 meters per second squared of acceleration. And look, we can solve for the normal force. So we now know the normal force would have to be equal to 24 times 100. And then I'm going to add 980 to both sides. And I get this big normal force of 3380. 3380 newtons. All right, so I now know the normal force. I know the force of gravity. And so we can actually calculate our G's. The best way to think about G's a G, the G's are just the ratio of, in this case, the surface is pushing on the person. And how's that surface compared to its normal gravity, Fg? Well, we write it as a ratio. And so the normal force is 3380 newtons. Fg is 980 newtons. And when I evaluate that, we get our G's. All right, so I get 3380 divided by 980. Those riders are experiencing 3.45 G's. They're experiencing a multiple 3.5 G's. All right, so they feel 3.5 times their normal weight. So that passenger would experience, if they look down at that scale and it normally would say 100 kilograms, it now says 345 kilograms. All right, so a lot of G's. They're going to feel pressed into the floor because that normal force is pushing up on them. Now, some of you might be wondering, what about the other passengers? Right? We calculated the G's on a 100 kilogram passenger. We kind of arbitrarily picked that number, right? But surely not every passenger is 100 kilograms, and there might be multiple astronauts in this vomit comet going through this bottom part. So what do they feel? Well, let's see what happens when we apply a different mass. And anytime we have something that's an unknown, we can keep it as a variable. So if we set up our same equation, remember, the equation we used to solve this problem was that the sum of all the centripetal forces, which the normal force and Fg are the two forces that act along that centripetal axis, would cause that mass to accelerate centripetally. So that's our equation, and we can plug in the things we know, right? We still don't know Fn. When we found Fg, we really just took the mass times the acceleration due to gravity. Remember, acceleration due to gravity would be downward here, but downward is outward, right? So we're going to assign negative, not because it's down, but because it points away from the center of the circle. And on the right side, you have the mass, and the centripetal acceleration we found to be v squared over r, which is 120 squared over 60, which was 24 meters per second squared. And the centripetal acceleration is always inward, so it becomes positive. So I'll just put 24. And so now you look, you have an equation with normal force and mass. If we solve for the normal force, we would simply add 9.8 m to both sides. So you add 9.8 times m, right? I'm adding it to both sides to cancel it out from the left side. I would be adding 24m. And in algebra, we like to put the coefficient in front of the variable, so it just looks prettier. And you see, we can combine those like terms. So we find that the normal force would be 9.8 plus 24, so that would be 33.8. I'll be consistent, and I like doing our normal force in blue. So 33.8 times that mass. Right, so that's actually what the normal force is. And when we want to find G's, remember G's was simply the ratio of the force applied to the object given it the G's, which in this case is the surface, we'll call that the normal force, and gravity. And let's substitute what we have. Rather than an actual value for Fn, we have 33 times the mass, 33.8 times the mass, and we would be dividing that by Fg, which is 9.8 times the mass. And here you see that algebraically, no matter what we put in for m, it's going to cancel. And so really we get a ratio of those accelerations, right? And when I pull out my calculator and I do this math, I would have 33.8, and I would divide by 9.8, and lo and behold, hey, there it is, 3.45 G's. Right, so we see that, in fact, as long as that plane is maintaining the speed through that radius, everything with that plane, the plane included, would experience 3.45 G's. So this is why you can have multiple passengers inside this airplane as it's passing through these parabolic arcs, and every passenger will experience the same feeling, these G's, which are really just what the floor is pushing on them. When this plane is in free fall along the top of the arc, they would all feel 0 G's. The floor would not push back. They would feel weightless like they were in orbit. And as you go through the bottom of the arc, they would get squeezed to the bottom as that normal force is pushing up on them. They would feel heavier. right? And so these planes fly these arcs and can simulate different amounts of gravity. I'll zoom out here. You can see the work that we did for this problem. And there we go.